deals with few numericals on the current electricity part. The first question goes like this, that the storage battery of a car has an EMF of 12 volts. If the internal resistance is 0.4 ohms, then calculate the maximum current that can flow or that can be drawn from the battery. Now, obviously, it's a straightforward question. That is, you have the formula from Ohm's law, V equals RI. From that, you have the current to be equal to V divided by I and V divided by R, and so that gives us the voltage over here is 12 volts EMF divided by the resistance, that is zero point 0.4, and obviously the value comes out to be 30 amperes. Now in the next question, what you have is that you have a battery. This is the battery arrangement that is shown by a dotted lines enclosed within that dotted line. You have a 10-volt battery which is having an internal resistance of 3 ohms, and it is connected to a resistor having a resistance supposedly R. Now if the current that flows through the circuit is 0.5 amperes, then we need to obtain what is the value of R in the first case. So this is the first bit of the question where you have to obtain the value of R, that is the external resistance or the resistor that is connected to the circuit. This is a switch which is closed such that the circuit is running, and so you have to obtain the value of R. Now as you can see that R and 3 ohms, they are in series, so the total resistance is 3 plus R, and the total EMF in the circuit is 10 volts. So again, using this same formula as above, that is V equals RI, you have 10 to be equal to 3 plus R times of I, that is equal to 0.5, that has been given. So from that you have 3 plus R to be equal to 10 by 0.5, which is equal to 20, and from that you have the value of R to be 17 ohms, which is connected externally to the circuit. The second part of the question consists it wants to know that what is the terminal voltage of the battery when the circuit is closed. Now as the circuit is closed over here, that I am showing by the dotted circle or probably by the solid circle over here, the circuit is closed means the key that has been provided here is closed. Had the key been open like this, the circuit would have been open, but the key is closed over here like this, and that is why you have a closed circuit and the circuit is running. For an open circuit, obviously you wouldn't have a current flowing through it. Now because of this closure, the connection made, you have the current running through the circuit, and the current passes through this external resistance that has been provided, that is R, and that is what the terminal between the two terminals of the battery. Now if I take this point A over here and point B over here, the external circuit that is present between AB, you have the battery arrangement, but the external circuit is what the terminals or the external circuit lies between the terminals, and that is why you have the terminal voltage over there, and that terminal voltage is simply equal to the, as you know, that V is equal to R times of I. That terminal voltage is the resistance that was just obtained, that is 17 times of the current that is flowing is 0.5, and that is why this value comes out to be 8.5 volts. That is the terminal potential difference across the battery when the circuit is closed. Now in the third question, you have that in two parts as well, as we show you the circuit over there, that we have three resistances, 1 ohm, 2 ohm and 3 ohm. They are connected in series, end-to-end connection, and we need to obtain the total resistance of this combination, which is quite easy because R net is equal to R1 plus R2 plus R3 in case of series. So this is just The net resistance of the combination is simply 1 plus 2 plus 3, that is equal to 6 ohms, is what has been asked in the first part. Now the second part asks us that what will be the potential drop across each resistor that has been provided. Now the potential drop, because this is a series combination, the potential drop will be different, and they will add up to give the total potential that was provided to the circuit, which is 12 volts. So let's check that. Now let V1 be the potential across the 1 ohm resistor, V2 be the potential across the 2 ohm, and V3 be the potential drop across the 3 ohm resistor. So what we have is V1 is simply equal to I times of R1. Now I is the same for everything. Now first, in order to obtain this potential, we need to find I. Now what is the value of I? I is obviously equal to, I can write it over here, I is obviously equal to uh, the total EMF that has been provided, that is V, divided by the total resistance R, that is in this case this is 6. So I here is 2 amperes. Now 2 amperes is the current, and the resistance of the first one, that is R1, that I have written over here, is simply 1 ohm. So you have the voltage to be equal to 2 volt. And similarly, you can calculate V2 and V3, because V2 and V3, in case of series combination, the current across each of them will be the same. In case of V2, you have I times of R2, which is equal to, I is simply 2 amperes that was calculated, multiplied with 2 ohms being the resistance in this case, and that is equal to 4 volts. And similarly, V3, you can obtain it to be 6 volts. Now if you add them up, 2 volts plus 4 volts plus 6 volts, they are adding up to 12 volts, which is exactly the potential that has been provided by the source, and that is completely distributed over the circuit, considering the conservation of potential energy in this case. Now in the next question, you have a parallel combination, and in parallel combination, obviously the current that is in this parallel combination, we have a 2 ohm resistor, 4 ohm resistor, and a 5 ohm resistor connected in parallel, and we are provided with a voltage source, which is giving us a voltage of 20 volts, and from that obviously you have a current flowing through the circuit. Now as you know that the potential difference across these two ends in parallel combination across the ends AB, that remains the same. That means you have the same potential difference of 20 volts across the 2 ohm resistor, across the 4 ohm resistor, as well as across the 5 ohm resistor. So the only different thing that will be in case of each resistance is the current. Let the current through this one is I1, and through this one is I2, and from this is I3. That means the current here, the current I that is obtained, that gets distributed. Now the first part of the question asks us that what is the total resistance of the combination, or the equivalent resistance of the combination. Now in case of parallel combination, obviously you have the reciprocal of the net resistance to be equal to the sum of the reciprocal of the individual resistances, that is 1 by 2, 1 by 4, and 1 by 5. The LCM obviously goes to what does it goes to what does it go to it goes to 20. And so you have 10 over here, you have 5 over here, and you have 4 over here. So that means it is 19 by 20. That is the reciprocal of the net resistance. So the net resistance in this case will be equal to 20 by 19. Now this is the net resistance of the combination. Now if we are to determine the current, now in the second bit, what we have to determine is that the current, the overall current, and the current across each of those wires, or each of those resistors that have been provided. Now the total current is obviously equal to the total voltage divided by the total resistance. So the I is equal to the total voltage, that is 20, divided by the total resistance that was provided, that is 20 divided by 19. 19 can go up, so 20 is cancel out, and you have 19 amperes. Now this 19 ampere will be distributed across each of those resistors. Now because you know that the potential across A and B, across these 2 points, will always be the same, that means you have the same potential difference of 20 volts across the 2 ohm resistor. So that means I1 is simply equal to the voltage that is across that wire, that is 20 volts, which is this one, because A and B terminals are common. So 20 divided by the resistance in that case is 2, so you have 10 amperes of current to be flowing through that. Similarly, you for I2 and I3, in order to calculate that, you just have the 20 volts of supply and divided by the resistance, corresponding resistance in that case is 4 ohm resistor, and that gives us a current of 5 ampere. And finally what you have is I3, and you know it well because 19 was the total current. This has to be 19 minus 10 minus 5, so this has to be 4. So let's check that. 20 divided by 5 is obviously 4 amperes of current that is flowing across the third resistance, that is 5 ohms. Now in the next bit of question, we have the heating effect of the temperature coefficient of resistance, which tells us that how the resistance increases with the increase in temperature. Now you have 100 ohms of resistance of a given resistor at room temperature, that is 27 degrees Celsius. Now it is always ideal to convert it to Kelvin scale. So 27 is obviously 273 plus 27, that means 300 Kelvin. You will always have figures which are 27, 37 and like that in most of the problems, in most of the numericals, so that they add up to give a rounded number, that is 300, 310, 320, likewise. Now the question is that if the temperature coefficient, that is alpha, is supposedly for that material, for that wire or for that resistance, is 1.7 times of 10 to the power minus 4 degrees Celsius inverse, what will or at what temperature will we have a resistance of 117 ohms? Now the resistance obviously R at any final temperature is equal to the initial resistance times of 1 plus alpha times of delta theta, and delta theta being the change in temperature. So this is the formula, and you have the resistances over here. This is 117, the final value that is to be obtained for the final temperature, and the initial resistance was obviously 100. And so as you can see, this will just be equal to 1.17 probably, because um, I will be telling you why, because if this is 1.17, this thing, then 1.17 multiplied with 100 will give me 117. So I know this value. So this is 1.7 times of 10 to the power minus 4. Now 1.17, out of that 1 is kicked out over here, so what we have is 0.17. So this value is simply 0.17. Obviously I forgot the delta theta over here. Delta theta is to be multiplied with the second term, so we have a delta theta there, which is multiplied with that temperature coefficient alpha, and so alpha times of del theta, alpha times of del theta, it has to be equal to how much? Has to be equal to 0.17, and out of that you have 1.7 times of 10 to the power minus 4 over here, and delta theta is over here, so this is 0.17. Now from that you have del theta to be equal to 0.17 divided by, I can just take it as 0.17 as well, and you know, take the 10 to the power thing as minus 3 instead of minus 4, because one of the 10 goes down and you have you have 0.17 instead of 1.7. So now as you can see, these two terms cancel out, and what you have over here is just I hope I've done it right. Yes, I have, probably. And this goes to 1000. So you know, as the temperature over here was given in temperature coefficient was given in degrees Celsius inverse, so we need not use this 300 Kelvin. So what we can do is we just know the difference. Now the initial temperature was obviously 27, the final temperature, in order that the difference del theta is 1000 degrees Celsius, you have the final temperature minus the initial temperature to be that, and minus the initial temperature means minus 27 degrees Celsius, that is. And from that what you have is theta F, that is the final temperature, to be equal to 1000 plus 27. So this is simply 1027 degrees Celsius. That's quite a lot of temperature. Okay, now moving over to the next bit of question. If the current, negligible amount of current is flowing through a wire of length 15 meters, having an area of cross section to be equal to 6 times of 10 to the power minus 7 meters squared, and its resistance is obtained to be equal to just 5 ohms, then we need to calculate the resistivity. Now, as you know, the resistance R is equal to rho L by A. So from that you have to find the value of rho, that is equal to RA divided by L. That's quite an easy question. As far as the numbers are concerned, you can easily multiply them and find the value. You just place the values over there and there you have it. So this is just 2 times of 10 to the power minus 7. But what is the unit in this case? The unit in this case is obviously ohm meter, as discussed in the theory part of the chapter. These lot are the numericals for this video. We'll be doing few more numericals in the upcoming videos as well. Till then, thank you.